is of a Volvo that was actually purchased in 1991. And a few months ago, it made the news because this particular vehicle managed to surpass 1 million miles. The original owner had driven it, maintained it regularly, and at the moment that it clocked the 1 million mile mark, Volvo decided to award him with a free Volvo S60. You can actually Google that and read up about it. It's a pretty interesting story, but the idea behind this is that if you maintain your asset in a timely manner, then it will deliver good service. If the service is irregular and if we neglect it sometimes, then obviously it's going to be prone to breakdown. And in the worst instance, if it's never serviced and if repairs are ignored, then the asset becomes totally unusable. It becomes wasted expenditure. So the big question is obviously, what are we doing with our roads? If we're planning maintenance and undertaking the appropriate repairs, then we have a sustainable road network. It doesn't cost us a lot of money. It keeps the public happy. If we undertake maintenance in a more ad hoc type of manner, and if we sometimes neglect maintenance, then the costs start to rise. It becomes expensive, it becomes ineffective. And in the worst case scenario, if we ignore maintenance entirely, then the road asset becomes completely unusable. And what we're left with is a network where we have to do quite a bit of reactive maintenance. There's lots of emergency interventions that may be required. And when we consider the situation, and this is obviously a bit of an extreme example, but it's not an uncommon picture that we see in our road networks. We end up in cases where roads fail, potholes form, we get in, we patch the potholes, eventually the patches fail and we end up patching the patches. Again, not an uncommon sight in SA, but one has to ask the question in a scenario such as this, what is the actual cost that's being spent on this particular road? If you add up the maintenance cost to get in there, dig up the road surface, put the patch in, all of the times that the guys came in versus undertaking routine maintenance from the very beginning, it's effectively chalk and cheese. So it pays to have a good maintenance plan and a good maintenance program in place so that we can avoid unnecessary and wasteful expenditure and rather use that money somewhere else where it would be more valuable. Maybe not necessarily on the road network fixing other roads, but you could use that same money in other departments such as maybe education, water, or even energy for that matter. So when we consider road asset management and we ask ourselves, what's the silver bullet? How do we get this right? The formula it's actually pretty simplistic. It's not anything difficult. Road asset management is all about doing the right treatment on the right section of road at the right time. However, to achieve that formula, it can be a little complex to achieve. If we look at the conventional approach to undertaking data collection in terms of understanding the road, it's important to know that if you want to get the right treatment, the first thing that you have to do is know what the actual condition of the road is. Historically, engineers or experienced assessors would have typically taken the clipboard and either walked the road or undertaken a windscreen survey where you drive the road at low speeds, typically between 20-30 kilometers per hour, and you'd physically record the distresses according to the TMH9 visual inspection sheet. The challenges with that is that firstly, it's a highly subjective process. It does require experienced engineers to undertake the assessment so that the degrees and the extents of the different distresses are recorded accurately. It is also time consuming. Typically in an urbanized environment, one would be expected to achieve between 10 and 40 kilometers of assessments per day. When you consider that typically networks may be 5,000 to 8,000 kilometers long, you'd need a lot of assessors to undertake the assessments in a quick manner. It is also weather dependent. If it's raining, then it's a problem. You can't really work in the rain. Ironically, it's actually good to assess the cracks just after rain because you see them quite clearly. But safety is also a huge challenge when it comes to undertaking these types of assessments, because very often the assessor has to jump out, take measurements such as rut depths, as well as lane width measurements, and it does pose a certain level of risk to the assessors. I think one of the biggest challenges with this types of assessments is with respect to the acceptable level of tolerance. Typically, there is a 10% level of tolerance. In extreme instances, that does pose a problem, because if the senior assessor, as an example, rates the road and comes up with a VCI of, let's say, 60%, it means that another assessor who may be a bit harsh in his ratings may end up rating the road and ending up with a VCI of, say, 50%, and a less stringent assessor may end up rating the road and getting a VCI of 70%. Both are technically acceptable because they are within 10% of the tolerance. But if you remove the senior assessor from it, you now have a situation where assessor A has rated it at 50% and assessor B has rated it at 70%. That's a 20% difference. Effectively, one saying that the road's in good condition, the other saying that the road's in poor condition. Obviously, that's an that's an example which is pretty extreme. But the idea is that there's a lot of subjectivity when it comes to determining the road condition in purely a manual type of approach. Recently, there have been methods to look at digitizing the assessment or the ratings form, and it has been met with a slight improvement in terms of the accuracy. There's certainly speed advantages to undertaking assessments using a tablet with the built-in application of the TMH9 form, and it does reduce the number of errors, especially when you're transferring manual ratings to a digitized environment. However, the problem is that the process is still highly subjective. There are a lot of parameters of the distresses which relies on experienced assessors, such as rating the degrees and extents of the transverse and the longitudinal cracks, as well as the riding quality for that matter. You know, it depends on whether you're doing the assessment in a brand new Toyota Hilux bakkie with good suspension, or maybe an old worn down Nissan NP200 with a poor suspension. So those factors do end up coming into effect in terms of how roads are rated from a subjectivity standpoint. And obviously, if you've got the wrong type of condition data, then you're not going to be making informed and accurate maintenance decisions further down the line. Recently, a few road agencies have started to employ the use of network survey vehicles. They've been gaining popularity in South Africa, at least for the past decade, but they're used pretty extensively in other parts of the world. The network survey vehicle is utilized to collect a number of functional or surface characteristics and surface distress parameters. I think the most common one is called roughness, or the International Roughness Index, or IRI, and that's basically a measurement of how smooth the road is. It is an objective measurement, and there is a scale in terms of what the different levels of IRI mean. IRI is typically measured in meters per kilometer, and to give you an example, an airport runway may typically have an IRI value of less than 1 meter per kilometer. A fairly good national road may be about 1.5 to 2, and a poor road with quite a few potholes will typically be in excess of 4 or 5 meters per kilometer. Another parameter that they measure, which is pretty useful, is texture. The lasers are typically located in the wheel parts as well as one in the center. So the vehicle is able to measure texture across the lane width, and that comes into play when the road is bleeding or flushing, especially in the wheel parts. You can then determine what's the difference in texture between the wheel parts as well as in the center of the lane. The texture that's measured is macro texture, not micro texture. but it does show some very useful readings and is important for the road manager when he's making his maintenance decisions. All the systems are linked with a DMI, or a distance measurement instrument, which effectively synchronizes all of the sub components. There's also an inertial measurement unit within the vehicle, which measures the geometry of the road. So what it does is it tracks the attitude of the vehicle as it's going around bends. It determines what's the crossfall or the grade, as well as the horizontal and vertical curvature. The level of accuracy isn't as accurate as getting a survey on site with respect to the geometry, but it is accurate enough for you to determine areas of where there could be potential ponding or reverse cambers and that sort of thing. It's basically based on the actual motion of the vehicle. So if the driver drives smoothly, you get pretty good data from that from a geometry perspective. All of the data is synchronized with the differentially corrected GPS. And what that means is that any data that's collected and recorded is geotagged with an accuracy which is typically sub-meter. And then very importantly, there's also the imaging system, which, depending on the road manager's preference, the vehicle will be able to record images at predetermined intervals of either 5 meters, 10 meters, or 20 meter increments. And then what that does is it creates a video of the road, which can be used to post-rate the condition of the road back at the office. And then one of the most critical features is the LCMS, or the laser crack measurement system. The LCMS is capable of detecting cracks on the road surface as little as 1 millimeter wide. But with the built-in algorithms within the package, the system is also able to categorize and quantify the different types of cracks. All of this information is collected at traffic speeds up to 110 kilometers per hour. So there's lots of data and lots of information that can be collected very quickly, very objectively, which means that the time and accuracy is a lot faster than undertaking it in a manual sort of way. Within the vehicle itself, the package that's typically used in these types of vehicles do undertake real-time monitoring of the various subsystems. It does look a little overwhelming at first, but all of these subsystems is what the operator will be monitoring. So there will be a driver and an operator in the system. Typically, they'll be monitoring things such as the GPS. The vehicle will typically track around about anything between 10 and 16 satellites at a time. And it also shows the strength of the GPS signal. It'll show the imaging from the front as well as from the rear cameras. There are status messages that come up if any of the components are not functioning according to specification, or if they're not online at all. It'll track the grade and the crossfall and the camber, which will be populated in these graphs. And effectively, the whole system comes alive, and the operator will be monitoring these subsystems, where he can have a graphical display of the GPS as well as the road profile information. And it's fully customizable, so different operators can move the windows around so that they can view it in whatever way they find it to be most efficient. The importance of this is that if there are any problems with the data collection, the operator is able to identify it quickly, and they can either stop the survey or they can undertake any mitigating circumstances to get the system back online and running again. So the vehicle that you've just seen is called a network survey vehicle, but it's only capable of measuring what's happening on the surface of the road. It doesn't tell you what's going on underneath. So the trained engineers amongst us will obviously argue that yes, but if we have an accurate condition of what's going on the surface, we can deduce what's happening underneath. For example, if we say rutting, if the rutting is pretty wide, then we know that the problem is further deep down in the pavement. And if it's a bit narrow and deep, then the problem must be higher up within the pavement structure. That's all fair and good, but it also helps to have a fully comprehensive assessment of the road network where there is technology that can measure what's happening underneath the road. At the moment, the FWDs or the falling weight deflectometers are pretty common devices, but the latest in terms of comprehensive pavement assessments are traffic speed deflectometer devices, such as the Intelligent Pavement Assessment Vehicle. The iPave is able to measure deflections, again, at traffic speed, at speed up to 80 kilometers per hour. And the way it does that is by utilizing Doppler lasers that's mounted within the trailer. The Doppler lasers measure the speed of the deflecting surface under the actual traffic load. So it's effectively measuring itself or the effect that it has on the pavement as it's driving across the road. In addition to the ability to measure deflections and subsurface characteristics, it's also able to undertake the same measurements that the network survey vehicle is capable of measuring. So in a single pass, the iPave can measure what's going on both above as well as beneath the surface of the road, resulting in a fully comprehensive assessment of the pavement. If we look at a little bit of the theory in terms of how it works, this is just an image of the rear axle and a slightly magnified view of the lasers that come through the trailer. That axle in the back is as close to a standard axle as possible. I think the weight in the back is about 8.4 tons. And the idea, again, is to mimic the standard axle. But it does utilize Doppler lasers that's mounted within the beam. So Doppler lasers do not work like traditional distance offset lasers. Instead, the Doppler laser uses light, and what it does is it splits the beam of light into two. One of those beams is kept within the laser, sort of as a reference beam, if you can call it that. And the other is emitted and it hits the road surface. So as it hits the road surface, remember the surface is moving with the load. So as it moves and the light hits the surface, the wavelength of the light changes, and that's effectively what's called the Doppler effect. This light is then taken back into the laser and compared with the original light beam, and the difference in the results of those two end up in what's called the fringe pattern, when you end up overlaying the two light frequencies over each other. And the distance between these fringe patterns can determine the velocity of the deflecting pavement very, very accurately. It does this at a very high data rate. It can sample the road at about 1,000 times per second, typically more than 900. From a quality perspective, if that drops to anything beneath about 500, then the data and information is discarded. This is just a slide or an illustration rather of how the lasers are fitted within the trailer and what they're measuring. So again, they're measuring the speed of the deflecting pavement, which results in the slope, and then through an integration method, that will then determine what the deflection goal is, which is the yellow line. The laser that's located in the front, very much to the right of your screen, is called the reference laser, and that's effectively used to determine what the original undisturbed state of the road is before the deflection actually has some sort of an effect on it from the rear wheel. So the slide does look a little bit busy, but I'll explain it very briefly. Effectively, as the vehicle is moving from left to right, it's placing a load which is well, it's a vertical load, but it's also traveling at a horizontal velocity. The lasers that are positioned within the beam are positioned at a slight angle, as close to 2 degrees as possible. And because we've got both a horizontal and a vertical velocity, we're able to then determine what the deflection slope is by dividing the two. And by determining the speed at which the pavement is actually deflecting, we're then able to use that and convert that measurement to obtain a pure pavement velocity and therefore a pretty accurate deflection slope. What's the interesting thing about this is that by adding lasers behind the load, we can get a full picture of the deflection ball. And some of the latest research actually shows that the maximum deflection, which we assume is directly beneath the load, is actually about 50 millimeters behind the rear wheel. And this has been proved time and time again with the lasers offset behind the wheel. There'll be quite a bit of research coming out and some papers that will be presented in the coming months on that. But certainly, it's food for thought, especially considering that the historic or the general way of measuring deflections is with the FWD. Remember, the FWD is designed to simulate what a standard axle will do. This is the actual standard axle and it's measuring itself. So very interesting space to watch. From an accuracy standpoint, obviously none of this matters if the repeatability is not at a high level, or even the reproducibility for that matter. Each of the subsystems has got high R-squared values sitting between 97 and 98%. And holistically, overall throughout the other parts of the world, such as the US and the UK, there's been extensive tests done on various test tracks around the world, just to ascertain what's the level of precision and accuracy. It's now reached a stage, especially in the US, where the technology has been accepted. There are various state road authorities that have moved away from utilizing the iPave as a research tool, and now they're actually utilizing it as a network surveillance tool. Once the data is collected, obviously it has to come back to the office and it needs to be processed. There are processing applications which allow the engineer to analyze and scrutinize all of the information that comes in. The beauty about this is that all of the different data sets are collected in a single pass. So the data collection itself is pretty quick, but from an analysis perspective, it makes analyzing the information a lot more seamless because all of the data is integrated with one another. So in other words, if you're looking at a specific spike in the road, all of the information related to that spike will pop up. And just by simply clicking and maneuvering and playing around with the information, it becomes a lot more intuitive for the engineer to undertake an assessment of the road network. One of the critical parameters to measure are cracks. Cracks are important because it tells us a story about the pavement and how it's deteriorating, but it also provides us with an idea in terms of how to best maintain the road network. As I mentioned earlier, the beauty about the crack detection software and hardware is that the system can categorize and quantify the different types of cracks. So not only does it see it, it's also able to determine typically what's the degree of the cracking from a severity perspective. The problem with cracks is that at the moment, there isn't actually any international standards in terms of how cracks need to be classified. And there are different methods of measurement in terms of how to actually get a value for cracks. In South Africa, we typically will still stick to the degree and extent on the 1 to 5 scale. And utilizing these different methods, we could post-process the data and then apply some sort of formula to equate the different types of crack measurement algorithms and software to achieve a degree and an extent. But the point is that with the system at the moment and with no ASTM or AASHTO standards in place, there is still a bit of debate in the industry as to which is the best. There are draft documents that have recently been circulated, but we're basically just watching the space to see what the industry decides. This is just showing how the system utilizes the internal algorithms to produce crack information, and we can see that it basically will measure the road. It will look at it. It will then split up the road into various blocks, and then from there we can get the different types of outputs. And it's basically categorizing the crocodile cracks on the left, and then the longitudinal cracks in the middle, and the little transverse crack on the right. And it makes it a lot easier for the engineer to then make his maintenance decisions and even quantify the amount of works that needs to be undertaken on the roads. Again, just a little bit more in terms of the different types of cracks that are available. The one in the left was one of the first models, just called the crack percentage. The data as it was collected. So each of these images represents one snapshot from the LCMS. Typically, it's about 5 meters longitudinally by 4 meters transverse. And utilizing the post-processing software, there's various methods to ascertain the different degrees of the crack. And again, just splitting up the different crack percentages. In South Africa, typically we would use the South Australian method because that seems to correlate pretty much closely with our local TMH9 assessments. With this data, one of the challenges is that it's very big. Typically, the information is around about 5 gigabytes per kilometer, which is rather sizable. And processing this data is not an easy task. So fortunately, the developers, they've got some smarts built into them, and they say, okay, if we need more processing power, what we can do is leverage on other computers within your LAN network. And so as long as the computers are linked within the network and have basically got the application within them, the system's able to look at the network and determine which PCs have got resources available and then utilize them to process the information. What this does is it reduces the processing time drastically. With a typical standard i5 processor with 8 gigabytes of RAM, 1 kilometer of data could take up to about 30 to 40 minutes to process. But if it's in a network, then it'll typically take about a minute or two to process. This is specifically in terms of the cracking information. And again, with data, if we consider, South African road network is in the vicinity of about 160,000 kilometers of paved roads. We have to measure all of the roads, then it results in millions of points of information. What I didn't mention earlier was in terms of the frequency of data collected, the road is actually scanned at every 2.5 centimeters. Obviously, that's a lot of information, but when it's processed typically at 100-meter averages. But when you start to imagine all of that data, even at 100-meter average length per road, the data sizes are still pretty enormous. A typical 5,000 kilometer network would have about 120,000 lines of data in a typical Excel file for the road manager to go through. So managing this information is quite a bit of a challenge. Fortunately, we are in IR4. Cloud storage is more and more common, and the benefits of cloud storage is huge, apart from it being theoretically unlimited. From a security standpoint, it's a lot safer than local area networks, in my opinion, that is, as well as it being backed up. There are cost implications in terms of storing and retrieving the data, so it's important that it's managed properly. But again, this is where we are. We are in the data age, and road asset management is all about practicing good data management skills, because that's where all your information is. If you want to make informed decisions, you have to have good, credible data at your fingertips. So once the data is processed and extracted in all of these Excel files, and you're looking at typically tables and numbers, it becomes more easier if we can visually look at the data. And so with that information, if it's thrown onto the cloud, it can be accessed pretty easily from a platform with a Google Maps background, where you can show the different roads and obviously color coded in terms of the different degrees of distress. All of that data can then be pulled out and basically accessed from the internet. As long as you've got a decent and stable internet connection, you could physically drive the road from behind your computer screen, which means that there's no high costs involved in you getting out to site to look at the condition of the road. You've got everything basically at your fingertips. And again, you can also utilize the toolkit to undertake basic measurements, items such as lane width, guardrail heights, asset inventories, and those sorts of things can be undertaken once the information has been digitized and stored in a cloud platform. I think very importantly for the road manager, it's about identifying which roads to fix and when. Basic road asset management from a filtering perspective, you could identify roads as an example here. We see which are the resealed candidates. Fully customizable filters allow the road network manager to select candidate projects and basically customize how he or she wants to go about in identifying which roads need to be maintained based on their current condition. These filters can be saved and accessed at a later stage. Once that happens, then the data can also be downloaded and submitted to the pavement engineer to undertake pavement designs. The difference in terms of having this sort of technology with the exceptionally high degree of resolution versus the antiquated sort of manual method is that because the resolution is so high, the data from the network assessment is now often being incorporated into the project level applications, because not just of the high degree of resolution, but also because of the number of different parameters, as well as the relevance of the information from a design perspective. It really helps the engineer to make more informed decisions in terms of how to maintain the network. This is a good example of what I'm trying to illustrate or trying to get across. Typically, the pavement engineer would have undertaken a deflection measurement, let's say at 100-meter intervals. And so in this 10-kilometer section of road, there would have been just 100 deflection points. It is possible that that spike may have been missed, and maybe that spike could have been missed because deflection points could have been taken on either side of them. What that means is that when this road is being designed, these sections of road may require a little bit of strengthening perhaps, or there may be a problem outside the road which needs to be addressed, which may not have been picked up at the time of the original assessment. But with the high degree of resolution that's being measured and recorded and scanned with these vehicles, these things now become a lot more easier to pick up and identify and assess. And so from a design perspective, it makes the engineer's job a lot more accurate, not just easier, but more accurate. And so they can hone in on their designs and make more economical design sense. This is just showing a little bit of repeatability and the difference between undertaking a mechanistic design using the FWD as well as traffic speed deflectometer data. There is a paper that was written on this, and this is just summarizing some of the findings from that paper. And I'll draw your attention to the last column on the table at the bottom in terms of the capacity or the million equivalent standard axles that were calculated utilizing both the FWD as well as the TSD data. We can see that on this 36-kilometer stretch of road, there were 3 uniform sections. And when the analysis was done, there's a pretty good correlation between the two. We're looking at about 0.1 million difference in the MESAs for the first section, almost similar data for the second section, and about 0.6 million standard axles for the third section. So the data can be used at the project level stage. It is being used at the project level stage. One could argue the differences between these two was based just on the FWD. It's giving a lower reading, but again, compare what the FWD is measuring versus what the IPAVE is able to measure. It is possible that because of the higher degree of frequency, the IPAVE is giving a much more accurate result because it's averaged a lot more data. This is what I was referring to earlier in terms of identifying problems before they even become visible to the human eye. If you're looking at these images, there really isn't much that one could see from the forward and the rear camera images at the top of this image. But if we consider the deflection data and we note the spike, something is clearly happening at that portion of the pavement, and we can even see that the cracks, there are very minimalistic fatigue cracks that are forming. When we start to combine that with the GPR information, we can see that there is clearly something going on beneath the surface of the road. It hasn't yet manifested into something. One of the reasons is that there's possible moisture ingress, and that obviously needs to be looked at sooner rather than later. If we can identify these problems early on, then it means that the road network manager has got more options available in terms of how to address it. If he has budget and resources available, then he can go out there right now. Alternatively, if he knows about the problem, then it means that he can choose to defer the maintenance to a later stage if he wishes to do so. But the important thing is that he knows about it well in advance to prevent any problems from happening. Closer to home, this is one of the local roads that we've tested. This was in 2018, February. And we can see the data shows the clear change in texture. With this table on the top right, you can see the sharp drop in texture. That's a new surface, and it's clearly visible at this point as we're approaching the new surface. The graph in the middle shows the deflection data. It doesn't look good because if we go further down the road, which is supposed to be a new surface, it seems to get a bit high compared to the road behind us. We look further down the road, round about, what is this, kilometer 9, we can see that the deflection data is a bit high. It is still the new surface. This was measured before the line marking went on, and the surface looks fairly good and fairly uniform. But the deflection data is quite high. Typically, for this sort of rehabilitation measure, it should be between the 300 to maybe 500 mark. We're sitting at about 1,500 microns. If we fast forward just 18 months on a newly maintained road, we can already start to see the distresses that are occurring and that's being picked up. So what this says is that utilizing the tech, it's able to identify these distresses well in advance, and it affords the road manager time to be proactive and sort these issues out rather than being reactive, and obviously meaning that it's a lot more costly to undertake the appropriate maintenance activity on the road at the right time. One of the other applications of the technology is in the construction space, specifically with respect to IRI. Those that undertake a lot of SANRAL work and some provincial work would be familiar with this table, whereby it's an incentive to the contractor to build the road to a good level of rideability. And obviously this has an effect in terms of the deterioration curve that I had showed earlier. If the road is built with a low IRI or a very good rideability, then it will, in all likelihood, have a longer lifespan versus a road that's built with a poor IRI. Just a very quick discussion on this table. It's obviously an incentive to the contractor because there are bonus payments associated with that. So utilizing the technology, the contractor can measure the road and basically use it as a tool for QA. And if he sees that he's not getting the level of IRI that he wants, he can revise his methodology so that he achieves a higher level of IRI and ultimately will get a bigger bonus payment for that. Conversely, if he does not achieve the minimum threshold, then he's subject to a penalty payment until such point that there's a rejection and he has to effectively rework the layer and or the surfacing. So contractors are starting to look at procuring the technology as well because it incentivizes them to build better roads. So that's a good initiative. One of the less common uses of the data and the information is by financial auditors and basically the finance house of road agencies, whereby they have recently begun to look at utilizing the data for updated valuation purposes. From a finance perspective, the road network is obviously an asset. It has to be valued regularly to determine both the current replacement cost as well as the depreciated replacement costs for financial reporting, and ultimately determine when the road asset needs to be replaced or rehabilitated. This is also directly from the TMH22, which shows the process and the procedure in terms of calculating the depreciated replacement costs as well as the current replacement costs. One of the biggest challenges that road agencies have is with respect to accurate as-built data, even financial records for that matter. We've worked with road agencies where, 2010 is not really that long ago, but the financial records before that are in a very, very poor condition, or they don't exist. From an inventory perspective, particularly, a lot of road networks or road managers have a discord between the asset register versus the GIS inventory. And when you can't manage your asset if you don't know where your asset is. So it's very, very crucial that the asset inventory is updated and it talks with the GIS shapefiles, and the asset register and the network inventory needs to be aligned. But the point is that the data from the technology, especially in terms of the condition assessments, are now a lot more accurate, and it allows the financial auditors to determine the replacement costs a lot more accurately versus utilizing subjective information in doing so. I think most importantly, the data is also utilized from a safety standpoint. If we follow the safety situation globally as well as in South Africa, we lose around about 12,000 people per year on our roads, which is significant. It's not to say that all of these people lose their lives because of poor road conditions, but having the information at hand, although it's primarily utilized from a network maintenance perspective, the data is also utilized to undertake network level safety assessments. So I think one of the benefits is that instead of undertaking a completely separate survey to look at the road network from a safety standpoint, because the information has already been collected as part of the PMS and road network management, that same information also has another use in terms of identifying where there are inherent safety concerns in the road network. One of the tools is the International Road Assessment Program, or commonly known as IRAP. South Africa does prescribe to IRAP. We've got the SARAP or SARAP, whereby the road networks are assessed in lines with the UN Decade of Action 2021 to 2030, which aims at halving road-related fatalities and serious injuries. The way that it works is by utilizing the information, the road assessment engineer or technician is able to measure the distance to roadside objects, things such as lane widths, are there guardrails, is the asset inventory in place? There's approximately, there's actually about 76 roadside attributes that are assessed from a safety standpoint. The road gets, coded. It then goes through a vigorous quality control procedure, and the data then gets uploaded into a free online platform called VIDA, where the road becomes star rated. Star ratings are basically just a 1 to 5 scale of how safe a road is, 1 star being extremely unsafe and 5 stars being extremely safe. May not necessarily be a situation whereby a road network would want all of their roads to be 5 stars, because that could be a bit expensive to attain. But typically road agencies would have policies that say, okay, let's aim for at least 90% of our road network to be 3-star and above. And that becomes a lot more manageable. And it becomes simple things such as implementing guardrails in the correct spots, sorting out things such as line marking, delineation, making sure that the roads are lit up, are there sidewalks in place, and a whole host of tried and tested safety related features. This this illustration that you see in front shows the existing condition of the KZN road network on the left or on the top, and it shows that at the moment only about 44% of the road network has achieved a 3-star or better rating. However, if the department proceeds and implements the countermeasures associated with the assessment, then that number can be increased to about 93%. What that effectively means is that approximately 20,400 fatalities and serious injuries can be avoided if these countermeasures are implemented. Similarly, for the Free State, it's presently sitting at about 48%, 3-star or better. But again, by implementing the countermeasures, that number can come up to 91%. And this is important because a lot of people don't understand the economic value of making roads safer. The CSIR did a study recently where they undertook an exercise to determine the actual cost of road traffic crashes to the economy. The initial study undertaken about 6 years ago showed the cost to be about 142 billion rands to the economy each year. A few years later, that number shot up to about 168, if I'm not mistaken, and now the number sitting in the vicinity of about 180 billion rands to the economy. Now, that number is pretty substantial. If we can make our roads safer and reduce the number of accidents and fatalities, that number comes down. I mean, at the moment, it's sitting probably at roughly about 3% of our GDP. Even if we make a 1% saving to the GDP on that, that's a lot of money that can be used to maintain roads and make them even safer, or even utilize that budget in other industries such as water, or even education, health for that matter. So it quite literally pays to make our roads a lot safer. And again, just to sum up in terms of road safety, the data is utilized to undertake an investment program, or a SRIP, a Star Ratings Investment Plan. And what that then does is it identifies which are the cost beneficial activities for the road agencies to undertake. If there's limited budgets, the program can tell you where the priorities are and which ones to focus on. But ultimately, it's about ensuring that something gets done. There's no point in collecting all of this excellent information and producing these beautiful reports if it's going to sit on somebody's table and nobody's going to implement it and do something about it. And then it's about undertaking continuous monitoring to see and understand what is the effect of that investment over time. Just as I get to the summary, it's pretty interesting to see how technology has transgressed and transformed over the ages. You know, in the 90s, we were undertaking windscreen surveys where we were physically looking down and physically recording what was going on the roads. And then as technology progressed, we started to basically drive the roads, get a video image of the road, and undertake post-rating in the office. Obviously, the benefit with undertaking the rating in the office is that the assessor is not subject to the environment and the safety issues associated with being on site. They're undertaking the assessment in a lot more stress-free type of environment. They could have a break whenever they feel like. More importantly, they could revisit the same road multiple times without incurring any additional costs of going out to site. So they can play back the road as many times as they like to ensure that the assessment is a lot more objective and accurate. And then as time progressed, technology began to identify these assessments. We're actually busy with a machine learning initiative at the moment, whereby the images are being processed by AI in the background to even further enhance the quality of the data, of the distress identification rather, so that the condition of the road can be rated now fully autonomously with an even much higher degree of accuracy and even more speed. And obviously, that's what it's all about. It's about knowing the network so that these maintenance advanced maintenance decisions can be achieved. And most recently, there's also the inclusion of LiDAR, which I didn't spend too much time speaking about. LiDAR is I'd say, making a comeback. LiDAR was tried out a few years ago. At that point in time, the accuracy levels weren't as good as they are today. If we go back about a decade, the LiDAR was typically spinning and collecting about 27,000 points in a point cloud per second. Today, that data is in excess of 2 million points per second. So there's a lot higher resolution with the LiDAR. It isn't quite at the level whereby it's capable of detecting cracks to this degree, or even measuring IRI to the level that the point lasers have at this point in time. But I'd say watch the space and give it about 3 or 4 years, and LiDAR will certainly be at that level where it can be used to replace the existing technology. But the point of this slide is that when we consider how technology has changed, it's just something to marvel at and be in awe at. And it's also something that we must be very mindful of and cognizant of, that when it comes to technology is not meant to replace the engineer. By no means is that the case. In fact, all of the technology it's just a tool in the engineer's pocket, so that the engineer can diagnose problems a lot more accurately and a lot more quickly. But just to sum up as well, when we look at utilizing this technology and digitizing the information, the main benefit is from an objectivity standpoint and a repeatability standpoint. It is scientific technology, it's information that can be collected multiple times over and still get an objective and accurate measurement of the road. Most importantly, it's various different parameters that are now synchronized and integrated. So it makes managing the information a lot better. And obviously with the multiple data uses, not just to determine what's the best maintenance strategy and save by making the correct maintenance decisions. There's also the safety benefit, whereby safety initiatives are identified and ultimately we save lives. In fact, as it stands, as of last week, there's 40 people in northern KwaZulu-Natal that are alive today because of the safety initiatives that have been implemented, primarily due to the data that's come out of these types of assessments. Even from a design perspective, engineers can now make those more honed in and more accurate pavement designs. So the roads now last a lot longer, and it becomes a saving to the fiscus. And ultimately, that's what it's about. It's about the saving to the fiscus, so that we can make well-informed maintenance decisions and be accountable for those decisions. So on that note, thank you very much for your time. And yeah, over to you, Peter.
Thank you, Yesh. That was truly excellent example there of using technology to solve a very real-world problem. In this case, relating to road asset management. Some of the key points that I took out from that was obviously the speed of the data collection and the accuracy of the data collection. Increased safety to inspectors who normally would be, as you say, standing on the road with the cones around them trying to do measurements, but now in fact they're safe because they're either in a vehicle doing some of the survey or actually sitting in the office. So big increase in safety to inspectors. Classification of road condition is now based on data rather than some kind of subjective form, which I think Yesh illustrated very well. And of course, managing the economics of the whole road network. Reminds me of that adage that if you can't measure it, you can't manage it. So I think this is a really good use of that technology. We'll have a look and see if there's any questions. I'll just see if I can see the Q&A. Just going through here. Okay, there's a question here for you, Yesh. What is the cost of the vehicle with all the equipment?
Yeah, very, very common question. It's a lot. So
it's a lot. Yes.
Yeah, so it's in the vicinity of about $3.5 million US, which roughly equates to about 45 million rand. But that's also inclusive of some pretty steep fees to get it out of the harbor. So SARS does take a fair chunk of that. But that being said, it's never the intention for the road agency to purchase the equipment. It's the benefit of it actually comes in the service offering. So it's better to procure the services of the equipment instead. Typically, it could cost, depending at the maximum, if you're collecting all of the parameters, it's typically about 3,500 rands per kilometer for the data collection. And then that can reduce if it's just one or two parameters that you're looking at, which really isn't feasible in the grander scheme of things. But I think from a cost perspective, one of the key things to note is that it doesn't really matter whether, as a road manager, you're paying 300 rand or 3,000 rand or 10,000 rand per kilometer for the data collection. The saving comes in the millions of rands per kilometer that you're saving by making the correct maintenance decisions upfront, and having that valuable information at hand goes very, very far. We did a pilot study on a sub network of about 80 kilometers just to try and ascertain the difference between a subjective manual assessment versus utilizing a very fully comprehensive assessment using the technology. And it showed about an 8 or a 10% saving in the annual maintenance budget. I believe that figure can be a lot larger, but even if you just take 10% on, let's say, R1 billion budget, that's already 100 million rand saved on undertaking the correct maintenance activity on the correct section of road. So just in that saving alone, it actually quite literally does pay to get fully comprehensive measurements of the road network. Yeah.
Thank you very much, Yesh. Thank you for that answer. Difficult question, that. Okay. Next question comes from Julius. What is the minimum crack width that can be detected?
Okay, so at maximum resolution, the crack width it can detect cracks as little as 1 millimeter wide. That's a lot of information to process, as well as to store and to manage. And typically you can't see that if you're doing a visual inspection in any case. So the general norm is to actually reduce the resolution to about 5 millimeters. And that's picked up pretty easily. It drops the size of the data quite substantially as well. And it's generally accepted from road network managers if that's the width to choose from. I will mention one of the drawbacks to the technology is that if the crack is actually filled and it's filled to the surface, then sometimes the tech may not pick that up automatically. But the technology does allow the user functionality to physically draw in a crack if it's not automatically detected.
Thank you, Yash. Okay, next question from Omar. Is there any estimate in, I think it means what the length of the road network should be to make it feasible to use the system?
That's actually a very good question, because at the end of the day, it is, it's horses for courses. And it also depends on what level of maturity you have when it comes to managing your road asset management system. You have a situation of whereby if you've got a small network, then it really isn't feasible to bring in something of this magnitude, because you could get a pretty accurate assessment of your network in a very short period of time. If your network's just a few 100 kilometers, I wouldn't necessarily recommend something like this. I would say that the threshold would be about 1,500 kilometers. If you've got anything beyond that, then certainly utilize something such as the iPave. But even if you've got a smaller network, you could use the NSV, and there's a whole host of other non-destructive technology that could be utilized on smaller networks as well. I think the important thing is that whether it's a big or a small network, the type of information that you get and how you utilize that is what's critical. So yeah, so on for the big truck, I'd say about 1,500 kilometers. And if it's smaller, there are other alternatives also available.
Okay, thank you, Yash. Next question is from Michael. How does the iPave take the effect of truck speed on the deflection measurements?
Yeah, that's a very good question, Michael. Lots of studies have been done in that one as well, because slower speeds and the road behaves differently. So it doesn't, it does take into effect of speed in terms of the actual speed that the vehicle is traveling. So the truck is able to travel at speeds up to 80 kilometers per hour. The measurement that it undertakes is the actual deflection measurement at the actual speed at that time of measurement. So if the vehicle was approaching a traffic signal and was slowing down at a constant rate from 80 down to, let's say, down to 40, it would measure the deflection of the pavement as the truck was slowing down as well. So it doesn't necessarily, or it does not report all of the deflection data at a normalized speed. That can happen after the data has been processed by the engineer if he or she chooses to do so. But the actual measurement is of the speed of the truck at the time of measurement. So that's the effect that it is having on the road. That's actually a good question, because the operators are also trained to mimic typical driving conditions as far as possible. So although it can measure at up to 80, if the road speed 60, it will measure at 60. They won't exceed the road speed.
Okay, thank you, Yash. Next question is from Carl. How can the network survey vehicle be modified to measure potential damage to agri products in transit along corridors? I'm not sure if that's clear to you.
It is. I'll have to apply my mind a little bit more. Hi, Carl. Thanks for that one. Can it be modified? I don't think it needs to be modified per se. I think that the data as it stands could be useful if you've got hysteresis. In other words, if you utilize it periodically, let's say on a weekly basis for 8 weeks, or on a fortnightly basis for 3 months or something of that sort, then you'd have historic data to undertake comparisons on, and you could then sort of determine what the actual deterioration model would be based on that. We've done similar studies elsewhere from a pavement performance management perspective, where on a quarterly basis, we've been monitoring trial sections on different types of different asphalt mixes. And that was basically utilized to determine the potential strength of the mixes and what the durability of them were. So in your instance, to look at the potential damage, I'd say that if you look at it from a continuous monitoring perspective, you'd then be able to plot the deterioration and come up with some sort of a model. Obviously, looking at external factors as well, such as environmental, seasonal factors and stuff like that as well. I hope that answers it.
Yeah, okay, thanks, Yash. That was, you said, difficult question there. Okay, the last question that we've got here is from Dudley. Dudley is asking, how do we go about implementing such a system, taking, for instance, a province like Free State? A decision in principle, but that would need some idea of costs, which include the system needed to implement and manage the process. I think that's quite a difficult question to answer, but be your best shot, yes.
Yeah, so I think one thing that's important to also remember is that the data collection is only one part of the pie. As I mentioned earlier, you can collect this information, but if nothing's being done to actually implement the maintenance activities, then it's effectively all done in vain. You might as well just use an Excel spreadsheet to sort of manage the network. So yeah, the data collection is one piece of the pie, but it's, I would argue, probably the most important piece of the pie, because everything that follows beyond that is based on having credible information. So it's a bit difficult to answer that one, because there are external stakeholders that need to be brought into the mix as well. And yeah, they from an implementation of a system standpoint, I think, if I get this right, and if I'm answering a question, I think that it just depends on what's the department's internal policies that are in place to allow the system to come in. What I can say is that there is provision within the Provincial Roads Maintenance Grant, as well as the Rural Roads Asset Management Systems grants, that make provision for this type of data collection, as well as this type of, not necessarily say technology, but this type of analyzing information in support of road asset management systems. So even the practice note, which talks about best practice and guidelines to manage towards road asset management systems, does speak about utilizing technology such as this to undertake the data collection, and beyond that, to select appropriate maintenance strategies, as well as the implementation and the full asset management life cycle. So read in conjunction with the DORA in terms of the PRMG, as well as the practice note, there are those provisions that could be the start point to be the catalyst to implement these systems, not just in Free State, but in all provinces and municipalities as well.
Yeah, thanks, Yash, for that. Okay, that's the end of our questions. There's been, I just want to mention, there's a comment here where both Ferdy and Sibusiso are saying this should be shared with the Transport Division. Just to let you know that, in fact, everyone in SAICE actually was invited to this webinar, and specifically, as well as the IT Division, of course, the Transportation Division did get an invitation as well. So Ferdy and Sibusiso, rest assured that they were invited. Okay. So I think we'll do a final sort of wrap up. I would like to thank Yash Yesh Balaram very much indeed for his excellent presentation to us this afternoon. And also to acknowledge the time and effort spent in preparing such a presentation. SAICE IT Division greatly appreciates this, Yesh. Thank you very much indeed. And of course, events like this don't always just sort of come together by magic. I'd like to thank Debbie for making all the arrangements and for organization of this webinar. And lastly, to thank everyone who attended this afternoon. We've had a really good turnout. And thank you for making the time. And we hope that you have learnt a bit more than you knew at 4 o'clock this afternoon. So lastly, if you'd like to join the IT division, the SAICE IT division, and sister committee in wonderful things that we try and do to assist our members, then you can do so by contacting Debbie Besseling, and we'll be happy to connect with you. To be able to contact Debbie, and she will then put you in touch with us. So thank you very much indeed, everyone. And further ado, thank you, Yesh, for your input this afternoon. We'll end the meeting. Thank you, and have a safe evening and good night.
Thank you, Peter. Thank you, David. Good night.
Yes, thanks so much, and thanks, Peter, as well.